In the last lesson, we discussed the circuit model of calculations and introduced some elementary logic elements, namely the elements NOT, AND, OR, and XOR. Let us consider on their basis the simplest switching circuits to add numbers. The slide shows the basic element of such schemes, which is called a half adder. The half adder adds two binary numbers, each of which can be either 0 or 1. These numbers are fed to the input of the half adder in the form of bits A and B, and as a result of all logical operations, we also get 2 bits at the output. The first of the output bits will be equal to the addition modulo 2 bits A and B. And the second bit will be the so-called carry bit. It will correspond to the next digit of a binary result of summarizing. In fact, it is very similar to the addition in the column, when we just write the first bit and remember the second bit taken further into account. For example, if both the A and B bits are equal to 1, then the result of their addition is 2, which is the binary number system is written as 1, 0, and it's already a 2-digit number. The first bit corresponding to the 0 digit, in this case, will be equal to 0, and the carry bit corresponding to the first digit will be equal to 1. If, for example, bit A is equal to 1 and bit B is equal to 0, then the result of the addition will be 1, which is 1-digit number, but which, of course, can also be written as a 2-digit number, 0, 1. Naturally, 0 in this case does not carry any useful information. The scheme of the half adder is presented on the slide. In the first step of the operation of such a half adder, copies of input bits A and B are created. Then, one of the resulting pairs of bits A and B is fed to the input to the AND element, and then carry bit C is obtained. As we were convinced earlier, bit C should be equal to 1 if and only if both A and B bits are equal to 1, and the AND element will provide us with just such a result. Another pair of bits A and B is fed to the input of the XOR element, exclusive OR, which, as we found out in the previous lesson, modulo add 2 bits to the input. Thus, we get 2 bits, each of which will represent the corresponding digit in the binary notation of the sum of bits A and B. To fully describe the work of the half adder, let's write down its truth table. So, let's construct the truth table for half adder. At the input, we have bits A and B, and at the output, we have bits C and A plus B. So, let's consider all possible variants of input bit values. It's 0, 0, 0, 1, 1, 0, and 1, 1. And complete the truth table. When both of the bits at the input are equals to 0, then the bit C also equals to 0. If bit A equals to 0 and bit B equals to 1, or bit A equals to 1 and bit B equals to 0, bit C equals to 0. And if both of the bits at the input equals to 1, bit C equals to 1. Now let's calculate the sum of the input bits. It's 0, 1, 1, 0. And here we'll write down the result as a binary number. Here we'll write down the result as a decimal number. So, what we have now? 0, 0, 0, 1, 0, 1, 1, 0. This binary numbers corresponds to the decimal numbers 0, 1, 1, 2. However, one half adder for bitwise addition of number turns out to be insufficient. As with the addition in a column, if it turns out that the previous step the results exceeded the digit capacity, then we need to take this further into account when adding the numbers of the next digit. Thus, the next step can be associated with the addition of not 2 but 3 numbers, while the half adder has only 2 inputs. The slide that you see now shows a scheme of the so-called full adder, which not only adds the numbers a, b, but also takes into account the carry bit d from the last step. That is, actually adds a, b, and d. The adder presented on the slide consists of 2 half adders and 1 XOR element. Having a truth table for half adder for XOR element, let's write down a truth table for the adder. Now we want to write down the truth table for a full adder. To do this, we firstly introduce the time scale. So the moment t0 is input, the moment t1 is after the first half adder, the moment t2 is after second half adder, and t3 the variant. So we have bits a, b, and d at the input, and let's consider all possible variants of the values of these bits. 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, and 1, 1, 1. So, at the moment t0, the moment t1, we have 3 bits, the bit d, the bit a plus b, and the bit c1. So at the moment of type t1, bit c1 here equals 0, 0, 0, 1, 0, 0, 0, 1. Bit a plus b equals 0, 1, 1, 0, 0, 1, 1, 0, and the bit d still unchanged. So 0, 0, 0, 0, 1, 1, 1, 1. After that, at the input of the second half adder, there are 2 bits a plus b and d. So at the input of the second half adder, at the moment of time t2, we have bits c1, c2, and a plus b plus d. So the bit c at the input of second half adder is 0, 0, 0, 1, 0, 0, 0, 1. Bit c2 is 0, 0, 0, 0, 0, 1, 1, 0. And the sum of all 3 input bits is 0, 1, 1, 0, and 1, 0, 0, 1. And as a result, we obtain 2 bits, C3 and A plus B plus D. Bit A plus B plus D still unchanged, so it's 0, 1, 1, 0, 1, 0, 0, 1. And the bit C3 is 0, 0, 0, 1, 0, 1, 0, 1. So let's write down the result as a binary number, R2. 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1. And these binary numbers correspond to the decimal numbers 0, 1, 1, 2, 1, 2, 0, 3. To add numbers with several digits, you need to apply a cascade circuit consisting of others and half-others. Such a scheme is among the exercises proposed for independent work. That's all for now. Thanks for your attention.